Good day, everyone. Welcome to the part 2 of our discussion about work and energy. On this part, we will consider some examples on work, energy, and power. So stay tuned and hope you'll learn something about this. Okay, for sample problem number 1, we have this problem. The factory worker pushes a 30-kilogram crate a distance of 4.5 meters along a level floor at a constant velocity by pushing horizontally on it. The coefficient of kinetic friction between the crate and the floor is 0.25. First question is, what magnitude of force must the worker apply? Second, how much work is done on the crate by this force? Third, how much work is done on the crate by friction? Fourth, how much work is done on the crate by the normal force by gravity? And lastly, what is the total work done on the crate? Let us answer the first question. So what is the magnitude of force that the worker must apply on this setup? So what we are going to do is, first, let us identify the given. So in this case, we have the mass. The mass is actually equal to 30 kilogram. And then we also have this distance here is equal to 4.5 meters. Okay, and take note this speed here is constant. And then we also have the coefficient of friction, mu k. That is actually the friction between this ground and the bottom part of the box, and that is actually mu k is equal to 0.25. Now, to answer this, we try to establish first the free body diagram. So in this diagram, we have this human being is actually exerting a force F there, and then we know that friction is present at the bottom, so the friction is actually towards the left and should be denoted by Fk. And then we know also that there is a weight since the box has a mass, so gravity acts on it, and that creates a force equal to weight. And then of course, by virtue of Newton's third law, if the box exerts a force in the form of a weight on the ground will also exert a force towards the box in the form of a normal force. So bottom line is, if we establish the free body diagram, the free body diagram would look like this. So you have, this is the box, you treat the box as a dot, so we have the weight at the bottom, and then we also have normal force at the top, and then we have the external force that is applied by this human being, and the friction, kinetic friction, that is exerted by the ground towards the box. Now, we try to look to create an equation out of this free body diagram, and that is equal to this. We have summation of forces along the x. So we treat this horizontal line here to be our x, and the vertical line to be the y component. So we have summation of forces along the y also. So along the x, so we have the force on the right, since this is located at the right portion of the horizontal line, minus the kinetic friction, since the kinetic friction is actually pointing on the left, and that should be equal to mass times acceleration. So in this case, notice that at the left hand side, this is actually the net force along the horizontal line, and then we have ma. So this is actually by virtue of Newton's second law. Now, since in the given, a constant velocity would mean that the acceleration is actually 0. Okay, so this is why this is equal to 0. Okay, since v is constant. Okay, now let us call this as our equation number 1. And so if we do the same thing for the y component, so we have the normal force at the top, this is positive, minus the weight, and that should be equal to ma along acceleration along the y. This one here, acceleration along the x. Okay. But then, since the crate does not move along the y-axis, so basically this right portion here is also equal to 0. So that means that that's just equal to 0. So we call this as our equation number 2. So from here, we can say that, okay, so from equation 1, we have the force is just equal to the kinetic friction. And we know that kinetic friction is just equal to mu k times the normal force. Okay, this is our definition from our previous topic on Newton's laws. On the other hand, from equation number 2, we can also extract the information that the normal force is just equal to the weight. But the weight is just equal to mass times acceleration due to gravity. So in this case, we can actually answer immediately the corresponding value of the normal force. We just have to substitute the corresponding value of the mass of the crate, that's 30 kilograms, and then times the magnitude of the acceleration due to gravity. So in this case, this amount of force produces 294 Newton. Okay, so that's the normal force. Now, having this idea, we can immediately solve for the force F, and take note that is the question of part A. So we just have to use this information of the normal force, and since mu k is actually given, so we can substitute the value of mu k. We have 0.25 times 294, that should be 294 Newton. 294, no, that should be 294 Newton, and this yields 73.5 Newton. Okay, so this is the final answer. That's the value for the force that the human being must apply to the crate. For letter B, we are asked to solve for the work done on the crate by this force F. So we know already, we've solved already for the amount of F, and that is, you can remember, this is just equal to 73.5 Newton. Now, the work done is actually equal to this. So we know that by definition, work is just equal to the scalar product of the force times the displacement. But you have to take note that the displacement in this case is denoted by this magnitude L. So if you look at the directions of the applied force, so we see that the applied force of this human being to the crate is towards the right, and the movement or the displacement of the crate is also towards the right. So basically, the direction of the force and the displacement is the same. So that's why from this definition, we know that this is just equal to a magnitude of the force times the magnitude of the displacement, which is in this case equal to L, and we have cosine of the angle between the two, but the angle between the two is equal to 0 since the direction of the force and the displacement is the same. So bottom line is we can rewrite the equation to be F times L. So since cosine of 0 is just equal to 1, so this is just equal to FL. Now, we can simply substitute the corresponding values. So we have 73.5 Newton and the distance, which is actually equal to 4.5 meters. And if you calculate for the product of these two, the answer is just equal to 331 joules. That's the work. So for letter C, we have how much work is done on the crate by friction. So notice that previously we've discussed that the kinetic friction is directed towards the left, so that's Fk, and the force applied by this human being towards the crate is towards the right. So notice that the amount of force created by this human being towards the box and the kinetic friction that resulted from the interaction of the ground and the box is just the same. So I'm talking about the magnitude. The magnitude of the two forces are the same. However, the direction is different. So we've learned that the kinetic the external force is towards the right. This is towards the right. Towards right. But the kinetic friction is towards the left. So bottom line is, if we calculate for the work, so we have the work per fraction should be Fk, scalar product of Fk, and the displacement, which is actually L. Now, since the direction of Fk is towards the left, so that is why the work done here is just equal to Fk times L. Since the angle between the two is actually 180 degrees, so that means cosine 180 degrees, that produces the negative here. So that's why you have Fk times L. Now, this amount is just equal to the minus F, since we know that the magnitude of F and the magnitude of Fk are just the same by virtue of our previous example, times L. So bottom line is, if you calculate for the work done for fraction, kinetic fraction here, kinetic fraction, so this is just equal to the negative of 331 joules. This is the negative of the work done by this external force. So this is the answer. Now, for letter D, if we try to look at the work done, how much work is done on the crate by the normal force and by gravity. So notice that the normal force is actually directed upward and the gravitational force is directed downward. And when we compare these two forces to the displacement, we see that the displacement is towards the right. So the angle between them, between the displacement and the normal force, is 90 degrees, as well as the acceleration due to gravity force or the weight and the displacement is also 90 degrees. So that is why for letter D, okay, so the solution for letter D is that the work done by the normal force and the work done by gravity is just equal to 0. Again, the reason why the work done is 0 because the angle between the force and the displacement is equal to 90 degrees. Now, for the last question, okay, what is the total work done on the crate? So the total work done on the crate can be calculated by this. So this is the solution for E. So we have total work done should be equal to the work done of the individual forces. So we have the work done of the external force plus the work done of the kinetic friction plus the work done of the normal force, and lastly the work done by gravity. But since we know already that normal force and gravity has no contribution, so we are left with work done by the external force and the kinetic friction. But as we have learned, the work done by the external force is equal to positive 331 joules, while the work done by the kinetic friction is the negative of 331 joules. So that's why if you add the work done, the answer is 0. So the total work done is equal to 0. So let us have the second example. We have a sled with a mass of 8 kilograms moves in a straight line on a frictionless horizontal surface. At one point in its path, its speed is 4 meters per second. After it has traveled 2.5 meters beyond this point, its speed is 6 meters per second. So the question is, use work energy theorem to find the force acting on the sled, assuming that this force is constant and that it acts in the direction of the sled's motion. Okay, let's begin with recalling the given in the problem. So at first, we are given with the mass of the sled, that is actually 8 kilograms, and that we are also given with initial speed, that is equal to 4 meters per second, and then we are also given with the final speed, which is equal to 6 meters per second, and then the distance is equal to 2.50 meters per second. So now, since we are asked to solve for the force and we should use the work energy theorem, so we start with the work energy theorem equation, which is actually equal to this. So you have 1/2 mv final square minus 1/2 mv1 square. So we can actually factor out 1/2 m, and we have v square minus v1 square. So basically we can plug in the corresponding value of the mass as well as the speed. So we have v2 is equal to 6 meters per second square, and then the v1 is equal to 4 meters per second square. So now if you calculate for the result of this, so this one yields 80 joules. Okay, so that's the work done by this force that acts on the sled, and that force is constant. Now, since we are asked to solve for that force, so what we are going to do is this. Recall that from the definition, we know that work done is also equal to the force, the scalar product of the force, and the displacement. Since the problem specifies that the direction of the force and the displacement are just the same, so we can simplify this further into force times distance. So in this case, the distance is actually given, and we have calculated for the corresponding work done on that, and that is actually equal to 80 joules. So we can solve further for F. So when we solve for F here, we just divide both sides by D. So that produces F is equal to work over distance. In this case, that should be equal to 80 joules divided by the distance, which is 2.50 meters. So now if you solve for the corresponding value, that should give us equal to 32 Newton. So that's the amount of force that acts on sled. So for problem 3, we have a 2 kilogram block is pushed against spring with negligible mass and force constant K is equal to 400 newtons per meter, compressing it to 0.220 meters as shown below. When the block is released, it moves along a frictionless horizontal surface and then up a frictionless inclined plane with slope equal to 37 degrees. So the question is, what is the speed of the block as it slides along the horizontal surface after having left the spring, and how far does the block travel up the incline before starting to slide back down? Okay, so let us answer this problem. So in this case, we are asked to solve for the speed of the block as it slides along the horizontal surface after having left the spring. So you have to take note that when the box pushes the spring and it compresses the spring with this compression distance, which is equal to 0.220 meters, and then when it is released, it moves in a smooth surface. So that means that the friction here in the horizontal track is negligible. So we can assume that as it traverses this horizontal surface, the speed is actually constant. So when the object leaves the spring, the speed that is produced is constant. And to solve for that, we actually use the conservation of energy principle. So we know that by energy conservation, we know that the energy, mechanical energy total initial, is just equal to the total mechanical energy final. So the initial state is when the box is compressed, and when we try to examine the energy present on that, we know that the box is actually stationary, so the kinetic energy is zero, and for the gravitational potential energy, the gravitational potential energy is also zero, since we will set here this horizontal surface to be our reference point for the potential energy. So that would mean here the total mechanical energy present at initially is just equal to the energy associated with the elastic material, which in this case is the energy of the compressed spring. Now, when the block is released from the spring, so the energy present is purely kinetic, since we observe that the spring is not anymore compressed nor stretched, so therefore the elastic energy is zero, and the gravitational potential energy is also zero since the box is still in the horizontal surface. So that's why the energy present in the final state is just equal to the kinetic energy. So now, from that point, we can actually solve for the speed. And to do that, we just have to transform this equation or simplify this equation. So in this case, we can cancel out the 1/2 and we can solve for the corresponding speed. In this case, we can write it as kx squared over m. That should be equal to v squared, or v therefore is just equal to the square root of k over m times the compression x. So now if we solve for v, we just simply substitute the corresponding values. So we have, for the spring constant, we have 400 Newton per meter divided by the mass, which is equal to 2 kilogram. Okay, we take the square root of the quotient of this 2 and then multiplied it by the compression, which is equal to 220 meters. So if you solve for this, you will get 3.11 meters per second. So that's the speed of the box or the block when it leaves the spring. So take note that speed is constant as it traverses this horizontal surface. So how far does the block travel up the incline before starting to slide back down? So in this case, we will emphasize that our geometry becomes this. The box now is traveling with the speed which is given by part A, and when it climbs up this incline, that speed is the same because the horizontal surface and the inclined surface are smooth, or the friction is negligible. So we take note also that the friction is equal, the inclined angle is equal to 37 degrees. And so when this block here climbs up this inclined plane, so the speed is the same, constant, but gravity is acting on this. So that's why as it climbs up, the speed decreases until such a point that the speed becomes 0. So when it reaches that point, the block is temporarily at stop. So it reaches this maximum height from the ground. We denote it by h, and this is actually unknown. And we are asked about this distance, this hypotenuse. What is that value? So again, we use conservation of energy principle. That is, the total mechanical energy initial is just equal to the total mechanical energy final. But again, in the initial state, okay, that the point wherein the box is just to climb the inclined plane. So the height there is still 0, so the gravitational potential energy is 0. And then since the spring is not anymore present on that state, in this state the spring is not anymore present, so therefore the elastic potential energy is 0, but the kinetic energy is present, that is equal to 1/2 mv squared. Okay, so that's the only energy that is present in the initial condition. Now that should be equal to the total mechanical energy. Now the total mechanical energy, since the speed is now 0, so the kinetic energy is 0, and as we know also that at the final state or the final condition, spring is not present, so therefore the elastic potential energy is also 0. But since there is a height with respect to the ground, okay, so remember that we set the horizontal surface to be the point where the gravitational potential energy is 0, that's our reference. But in this case, the box is located at a certain height, so therefore the box acquires some potential energy. So now we can actually solve for h here, and this h will lead us to solving for s via trigonometric function. So let's solve for h first. That is, we try to work out this equation here. So in this case, we can cancel out the mass and solve for h. So in this case, we have h is just equal to v squared over 2g. So when you solve for, or when you substitute for the value, so we know that the speed here is equal to 3.11 meters per second, should be square, divided by 2 times the magnitude of the acceleration due to gravity. So now when you solve for h, the corresponding value for that is just equal to 0.49 meters. So that's the h. Now knowing the h, we can work out these trigonometric functions, and since we have this triangle here, right triangle, so this is now the h, which is equal to 0.49 meters, and we know that the angle is equal to 37 degrees, and then we are asked to solve for this s, so that's actually the hypotenuse. So to obtain the hypotenuse, we just apply sine function of the angle 37, so that is sine of the angle 37 degrees is equal to the opposite side, which is actually the h, over the hypotenuse, which is actually the s. So rearranging this equation gives us s is equal to h over sine 37 degrees. So now if you plug in the corresponding value of h, so you have 0.49 meters divided by sine 37 degrees, so you'll obtain s equal to 0.81 meters. So that's the final answer. So this is problem 4. To stretch a spring 3 centimeters from its unstretched length, 12 joules of work must be done. How much work must be done to compress this spring 4 centimeters from its unstretched length? So to answer this problem, so we have to take note that the work done on the spring is actually given by the change in elastic potential energy, that is equal to 1/2 k x2 squared minus 1/2 k x1 squared. So in this case, so when the spring is unstretched, that means that that is the corresponding equilibrium position. So the equilibrium position is the case wherein that is unstretched, so the initial displacement is equal to 0. So we are left with 1/2 k x2 squared. So in the first condition, we are given that 12 joules of work is done. So you have 12 joules is done to stretch that spring. So that would mean you have 1/2 k. So the stretching distance is equal to 3 centimeters. So that's times 10 to the minus 2 meters square. So in this particular case, we can extract an information of the k. So the k therefore is just equal to 2 times 12 joules over 3 times 10 to the minus 2 meter square. So when you solve for that, that gives us the idea of the value of the k, and when you calculate for that, that is just equal to 267 Newton per meter. So that's the spring constant. Now, that spring constant is the same with this second condition. When you compress that same spring, but the compression distance now becomes 4 centimeters. So what we are going to do is to use the same equation. Now in this case, the unstretched is still the case wherein the spring is in its relaxed position. So that would mean the initial position is equal to 0. So that gives us 1/2 k x squared k x2 squared minus 1/2 k x1 squared. So again, this is 0 here. So now we can actually substitute the corresponding value. So we now have the value of the spring constant. That's just equal to 267 Newton meter. And the compressing distance is equal to 4 centimeters. Should be square. Now when you solve for that, that gives you equal to 21.36 joules. So that's the final answer. Okay, for the last problem, we have this: the hammer of a pile driver weighs 3,800 Newton and must be lifted 2.80 meters vertically at constant speed in 4 seconds. What horsepower must the engine provide to the hammer? So to answer this, you have to take note of the equation of power. So we know that power is just equal to work over time. So I think this is straightforward, since we are given that this hammer here will actually exert a force downward that is equivalent to the weight of this hammer, which is 3,800 Newton, and the displacement is also downward, which is equal to 2.80 meters. So in that case, we can say that the direction between the force and the displacement is the same. So we can adapt this formula, which is work is equal to force times the distance. Okay, since cosine 0 is equal to 1, so we are left with force times distance, and then over time. So now, when we substitute the corresponding value, the force is 3,800 Newton, and then the distance is equal to 2.80 meter, and the time is equal to 4 seconds. So if you solve for power, this is equal to 2,660 watts. Now, since we are asked to solve for power in terms of horsepower, we know that 1 horsepower is equal to 746 watts. So what we do is we try to convert this 2,660 watts. Okay, so we multiply this corresponding conversion factor, watts, and that should be 1 HP. So if you solve for this, we will get 3.57 HP. Okay. So that's the amount of horsepower that the engine must provide to the hammer. Okay, thank you so much for listening. That concludes the entire chapter of work, energy, and power. So stay tuned for the next lecture video, which will be on the concepts of momentum, impulse, and conservation of momentum.